Welcome. Today, we're going to get into something really fundamental, a question that's at the very heart of computer science. What actually makes a problem hard? We're about to explore this incredible class of problems that, well, if we could solve them fast, it would literally change everything.
So it all boils down to this, a question you've probably felt in your gut. Just think about a Sudoku puzzle, right? If I hand you a finished one, you can check my work in, a minute? Super easy. But starting from a mostly empty grid and actually finding that solution, that can take forever. It's that huge gap, the one between checking an answer and finding it. That's the mystery we're diving into today.
Okay, so to really get a handle on this mystery, we need a starting point. We need a kind of foundational puzzle. One problem that perfectly captures the essence of this whole class of hard problems. And for us, that cornerstone is going to be the Boolean satisfiability problem, or as pretty much everyone calls it, SAT.
So what is SAT? Well, at its core, it's just a big logic puzzle. You get this logical formula, a statement made up of variables that can only be true or false. Your one and only job is to figure out if there's any combination of trues and falses you can assign to those variables to make the whole thing come out true. Just one winning combo. That's all you need to find.
Okay, let's start with a really simple example. Check this out. A or B. It doesn't get much easier than this. A and B are variables, right? And that or in the middle is our operator. All it means is that the whole expression is true as long as at least one of the things it connects is true. So either A is true or B is true, or hey, they could both be true.
So how do we solve this thing? Well, it's pretty straightforward, isn't it? We can just set A to true, and that's it. We're done. Because A is true, the whole expression A or B becomes true, and we don't even care what B is. We found a solution. And when we find a solution, we say the formula is satisfiable. Say, easy. All right, let's kick it up just a notch. Take a look at this one. A and B and not A or C. Now we've got a couple of new things going on. That and in the middle connects two separate little puzzles, which we call clauses. And for the whole thing to be true, both the first part and the second part have to be true. Also, see that little symbol in front of the A? That means not A. It just flips the value. So if A is true, not A is false. Simple as that.
Okay, so let's put on our detective hats and solve this thing. Let's just try an assignment. What happens if we set A to true? Well, the first clause, A or B, becomes true or B, which is definitely true. Great, one down. But now we have to check the second clause. If A is true, then not A is false. So the second clause becomes false or C. Uh-oh. For that to be true, our only choice is to make C true. And bingo, we've got it. A equals true, C equals true. We found a winning combo, so this formula is also satisfiable.
All right, now this is where things get really interesting. What about a formula like this? A and negation A. Just take a second and really look at that. What's it saying? It's saying A has to be true and A has to be false at the exact same time. That should feel a little off, right? It feels kind of impossible.
Yeah, let's break that down logically. There are only two possibilities, right? First, let's say A is true. Well, then the first part is true, but the second part, not A, becomes false. And true and false gives you false. So that doesn't work. Okay, what if we try setting A to false? Well, now the first part is false, and the whole thing is false again. See? There's just no way to win here. No matter what we pick for A, we lose. It's a total contradiction.
And this leads to a really important concept. This formula is what we call unsatisfiable. There is a deep, fundamental contradiction baked right into it, so no solution could possibly exist. Some logic puzzles are just plain impossible to solve, and this is how we prove it. Okay, so what if we're not feeling particularly clever, and we can't just spot the solution? What's the backup plan? Well, we could just try everything, right? Check every single possible combination until something works. That's what we call the brute force approach. And let me tell you, it leads you straight into a giant brick wall.
Now, the brute force method, or the truth table method, is super simple, and it's guaranteed to work. You just identify all your variables, let's say there are n of them, then you make a giant table with every single possible combination of true and false. The number of rows in that table is going to be 2 to the power of n. Then you just go down the list row by row, checking each one. It's totally mechanical, but man, is it slow.
And this is why it's a brick wall. Look at these numbers. If you have 10 variables, you've got about 1,000 combinations to check. Okay, a computer can do that. Now jump to 20 variables. Suddenly, you're at over 1 million combinations. And then look at 60 variables. The number of tries is 1.15 times 10 to the 18th. That is an astronomical number. We're talking more than a billion billion. The fastest supercomputer in the world would be chugging away on that for centuries. This right here is the exponential wall. Brute force just does not work for big problems.
Okay, but this is where the story takes a huge, historic turn. For years, computer scientists had this feeling that problems like SAT were hard, but they couldn't really prove how hard or why they were hard. That all changed in the early 1970s with an absolutely groundbreaking discovery.
The Cook-Levin theorem. This proved that SAT isn't just some hard problem. It is NP-complete. This was an absolute bombshell. It was the very first problem in history to be given this title, and this one discovery basically gave birth to the entire modern field of computational complexity.
So, what on earth does NP-complete actually mean? Let's break it down. The NP part basically means that if someone gives you a potential answer, you can check if it's right, really fast. Think back to our Sudoku puzzle. Checking is easy, that's NP. The complete part means it's the king of the hill. It's one of the absolute hardest problems in that entire NP class. And here's the kicker. The theorem proved you can take any other problem in NP and transform it into a SAT problem. This makes SAT like a universal translator or a master key. If you could somehow find a fast way to solve SAT, you could solve thousands of other important problems just as fast.
So once SAT was crowned the first NP-complete problem, it was like the first domino was set up. Computer scientists now had this powerful tool to start a chain reaction, proving that a whole bunch of other problems were just as hard.
And this amazing technique is called a reduction. The best way to think about it is like a translation. Let's say you have a new mystery problem. We'll call it problem A. If you can build a clever translator that takes any version of your problem A and turns it into a SAT problem, you've just proven something incredible. You basically said, hey, if I had a fast way to solve my problem, I could use my translator to solve SAT fast too. And since we're pretty sure nobody can solve SAT fast, it must mean your problem is also super hard. It's like proving someone is a great fighter by showing they can go toe-to-toe with the world champion.
And this is exactly how that chain reaction, that domino effect, works in practice. First, Cook and Levin knocked over the SAT domino. Then, other researchers figured out how to reduce SAT to a version called 3-SAT. So boom, the 3-SAT domino falls. It's also NP-complete. Then, someone else reduced 3-SAT to a problem about finding groups in a network, called the clique problem. Boom, another domino down. And this just kept going. This chain of reductions revealed that hundreds of problems that looked totally different on the surface, problems in logistics, biology, circuit design, were all just different faces of the same underlying hard problem.
So, let's bring this home. How do you, as a future computer scientist, actually prove that a brand new problem you're working on is one of these super hard NP-complete problems? Well, lucky for us, there's a standard two-step recipe you can follow.
Here it is. This is the blueprint. Step 1. You have to show your problem is in NP. This is almost always the easy part. All you have to do is show that if I gave you an answer, you could check it really fast, just like checking the Sudoku grid. Step 2, you have to pick a known NP-complete problem like SAT or 3-SAT and build a reduction from that problem to your new problem. If you can successfully do those two things, that's it. You've done it. You have officially proven your problem is NP-complete.
And this little study guide really brings it all together. Just look at the pattern here. For every single one of these famous problems, the description is a hard-finding question. Can you find a satisfying assignment? Can you find a clique? Can you find a subset that sums to T? But look at the verification method. It's always an easy checking process. Just plug in the values, just check the connections, just add up the numbers. That gap right there between the hard find and the easy check, that is the absolute hallmark of an NP-complete problem.
And I really want to stress this is not just some abstract theoretical math. These problems show up everywhere in the real world. Trying to create the most efficient schedule for university? That's NP-complete. Trying to figure out the shortest route for a delivery truck? Yep, NP-complete. Designing computer chips, breaking codes, protein folding, so many critical multi-billion-dollar industries are built around dealing with these incredibly hard problems. And that all leads us to, without a doubt, the single biggest, most important unanswered question in all of computer science. It's a $1 million prize question, known as P versus NP. We've been talking this whole time about this class of problems where checking is easy but finding a solution seems impossibly hard. But what if it only seems hard? What if we're just not smart enough yet? What if there's some magical genius-level algorithm out there waiting to be discovered that could solve all of these problems in a snap? If it turns out that P equals NP, well, our world would be completely transformed overnight.
And that, my friends, is a puzzle for your generation to solve.